Hey guys, here's the video for the first topic in our new unit on permutations and combinations. I'm going to kind of do a mishmash here of sharing the notes with you and kind of explaining where some of our numbers come from and how we get them, and then go through a little bit of work on the whiteboard so you have an idea of exactly what steps to do as we go through. So the first thing we're going to talk about is the fundamental counting principle. It's basically a fancy way of saying if I have multiple situations going on at once, how many possibilities could I have in those situations? So this first example on the first page is going out for dinner and seeing what types of possibilities I could have with an appetizer and an actual meal. Okay, so we got our 3 salads and our 3 sandwiches. How many possibilities could I have? So if you break this down really slowly and maybe pause the video, write this out, do whatever you need to do. Let's say you have the 3 salads options with the Greek, Caesar, and spinach. Each salad could then come with 3 sandwiches. And since each one has that, your total amount of options would be 9. The Greek and the smoked brisket, the Greek and the club, the Greek and the Cubano, and then you do the same thing for Caesar, same thing for spinach. Now that seems all great, but what about a situation where you had 7 salads, 9 entrees, and 5 desserts, like a pretty normal menu that you could have? Well, how many possibilities could you have if you had to break down, your tree this way every time? That would be kind of crazy. So let's flip to page 2 and see what the fundamental counting principle says. It says that if one task can be formed in A ways, A being some number, and another task in B ways, then both tasks can be formed in A times B ways. So using the larger salad, entree, dessert example, if we did 7 times 9 times 5, there would be 315 total options for me to choose from. Maybe why it takes a little while for you to actually decide what to eat when you go out to a restaurant after this is all over anyway. All right, so that is why you have so many more options that way, and that's how you solve it. So just a few examples to kind of skim through with you guys. Again, pause the video if I go a little too quick, rewind, whatever, and then let me know if there's any questions when we get into WebEx. But example 1, how many license plates are possible in Manitoba? How do we get that? That's a pretty big number. It's 17,576,000. Well, to actually get that, you take the number of letters possible, you take the number of digits possible, 26 letters in the alphabet, and there's 10 digits because obviously 1 through 9, you could also have the number 0 as well. So you need 3 digits and 3 letters. And one of the things that we start to really focus on in the fundamental counting principle and in our booklets to come is we're going to be looking at something that says repeat and cannot repeat. Okay, so this idea here, the can repeat and cannot repeat, I meant for that to highlight, but you guys get the idea. All right. So this is going to be super important. And the reason it becomes important is if I can repeat my numbers or repeat my letters, then I could have A, B, C up to Z. And then when I use, let's say, A, I could use A again if I want to. So there's 26 letters times 26 letters times 26 letters. Same argument for numbers. If I use the number 9, I could still use the number 9 again. It gets a little bit different when you can't repeat. If something gets taken away, you've then lost your number of options. But that is how you get the number of license plate options. So number 2, how many ways can a store manager hire for 3 positions given 12 candidates? This is now where you can't repeat. So if there's 3 positions in this job and you have 12 total candidates, if you hire person A, call them Bob, Bob has been hired. Well, now if you want to hire the next person, you can't hire Bob again for the same position. Instead, Bob is now gone. You could hire the other 11 people. So when I try to look at the number of options, there are 12 people after the first hire. Bob gets hired. Now there's only 11 people. Now Jim gets hired. Now there's 10 people left. So you cannot hire the same person. So even though it doesn't bring up the idea of can or cannot repeat, that is just more of a common sense concept that once you hire one person, they're not in that field of people anymore. So it's 12 times 11 times 10, not 12 times 12 times 12 for hiring positions. Number 3, how many outfits can you order if you have 4 choices of pants, 5 shirts, 6 pairs of socks? Again, you could repeat these, so you just multiply it, very similar to our salad example. How many 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5 if repetition's allowed, if repetition's not allowed? So if repetition's allowed, and you have 5 digits to choose from, right? We're only doing 1, 2, 3, 4, and 5. So you could have 1, 2, 3, 4, or 5. You could have 1, 2, 3, 4, or 5. You could have 1, 2, 3, 4, or 5. So you multiply those options and you get your final total. But what if you can't repeat? So let's say your first number was 2. If you choose 2 as your first number, you can't choose 2 anymore. How many digits do you have left? you now have 4 digits left. Then you choose the number 3, now you have 3 digits left. The reason you use the number 5 and number 4, etc., is because you have 5 options. When you take one away, now you have 4 options. When repetition is not allowed in the situation, and you end up with only 60. So when repetition is allowed, you have a ton more options every time you do it. When repetition is not allowed, you have kind of shortened your field and you have less options available in those cases. So that's the fundamental counting principle. It becomes kind of an important idea when we get into permutations and combinations, which is the overarching theme of our little unit here. So that's going to come back in the next booklet. Factorial notation is the second part of this booklet, and the one that I'm going to kind of focus on the whiteboard with you guys eventually. Okay, so factorial notation basically says something like this repetition idea, where if you take one thing in your total field, so let's say 12 people, 5 numbers, whatever it is, and you take one away and you're not allowed to repeat, what is your next number? Well, it's always, if you start with 5, your next number is 4. Then your next number is 3. Your next number is 2. If you're always taking one away. So if I did 6 people must be arranged in a row, how many different ways can this be done? I can't repeat the people because they have to be arranged in a row. So it'd be 6 times 5 times 4 times 3 times 2 times 1. You have 6 people at the start. You take one away. Now you have 5. You take one away, etc. There's 720 ways total for this situation. This can be rewritten as 6 exclamation point. The exclamation point is the shorthand form in math for 6 factorial. That is a fancy way of saying that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. How do I get these answers if I do these as a factorial? Well, I can actually find this with you guys on the calculator. I'm going to stop sharing the booklet, and I'm just going to quickly share with you my TI calculator. On the TI calculator, you can find it here. You go 6, you hit your math button in the top left corner, okay, where we go from fractions to decimals and cube roots and all that. But this time, you're going to use your right arrow and you're going to move over all the way to prob for probability. And you'll notice that on the 4th number down, you have the exclamation point. So 6, exclamation point, hit enter, and you end up with 720, which is exactly what we just got in the booklet. All right. On a regular calculator, let's say you had something like this. Okay, there's another option here, and I can't get everybody's calculator, so just let me know if you can't find it. You're going to go 6 PRB on this one. Some of them have stat, some of them have other ones, but this has PRB. And when I go on PRB, you'll notice that there is the exclamation point on the end there. Hit enter again. There's my 720. So play around with it, try to find it on your calculator for your factorial button. Obviously, the larger the number, the larger your answer is going to be. So 6 factorial, 7 factorial, etc. That's where you find it on your calculator. But you get that by multiplying one number down every time. There's kind of a general formula for this, or a general definition for this. N factorial, which is some number, is going to be in the natural numbers. We're not going to look at 0, and we're not going to look at negative numbers. That's why it's the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., up to infinity. And we've got 6 factorial as an example here would be n times n minus 1, which means it's going to be 6 times 6 minus 1. There's your 6 times 5. Times n minus 2, your 6 minus 2, etc. So that is basically taking any n number and going n, whatever it was, times one number down, times 2 numbers down, times 3 numbers down, all the way down to 1 every single time. There's one little note here that 0 factorial is equal to 1. It really doesn't matter. That's not something that we really talk about too much, but that is something that might pop up in a random example at some point. It's a definition that cannot be proved. All right, let's take a look at example 1. They want us to simplify these, and they want us to simplify this by hand without a calculator. So this is where I'm now going to jump to my whiteboard, guys. So if you have the booklet following along, that's great. And now I'm just going to stop sharing the booklet, and I'm going to go through the steps here on the whiteboard. All right, so we have example 1A, which is 11 factorial. 11 factorial over 9 factorial. Now, how do we simplify this without a calculator? Because that would be a very provincial exam type question. What we do is we always take the larger number first, and we break it down as a factorial. Well, remember, we always start off by whatever the number is, which would be 11 in this case, times the next number 10, times the next number 9. And technically that would keep going all the way down to 1. But I'm actually going to stop here. And in factorial notation, what you can actually do is stop at any point, put the factorial notation, the exclamation point, and what that assumes is that you would then have 9 factorial, which is 9 times 8 times 7, etc. So I'm just not rewriting that. Well, why does that help me in this question if I stop specifically at 9 factorial? Well, just like any other all or nothing question, I don't have a plus or minus sign anywhere. I can cancel the 9 factorials. Okay, so I broke down 11 down to here. It matched my denominator. Now I have 11 times 10, which is a pretty straightforward multiplication question. And that tells me that 11 factorial divided by 9 factorial is 110. If you want to practice on your calculator to find that button, this might be a good one to practice. And you would find that 11 factorial divided by 9 factorial is 110. Okay, so we'll go n plus 2 over n minus 1 factorial. N plus 2 is bigger. Okay, n plus 2, n minus 1, we're going to have n plus 2 being the bigger number. So we just keep rewriting, going down by 1 every single time until we reach the other side, whether it's the top or the bottom, right? You'll notice that B and C, or sorry, B is the numerator as well, but question C, the denominator is bigger. So you'd actually break down the denominator in question C. But this one is the numerator again, those cancel. And again, you can just leave this. You do not have to multiply through it all. You just leave it as your final answer. All right, n plus 2, n plus 1 times n. All right, a couple more to go here. I'm going to leave example 3 as kind of a tricky one for you. Okay, so you guys can go through example 3 on your own. Okay, it's proving left side to right side, and I want you to try to break down each factorial as much as you possibly can without using a calculator, and then go through the notes if you're having trouble with it. And now I'm just going to show you example 4. Okay, so example 4 is the last type here where it is, again, some sort of algebra with the ends. But this time you're going to notice we have an equal sign. All right, whenever something says solve, which this booklet does, it's saying that you're solving for the unknown or you're solving for the variable. And in this case, we're going to solve for n. Okay, before we do anything, before we multiply or do any sort of old equation stuff that we already know how to do, let's get rid of the factorials. Okay, so the first step in any factorial equation question is to get rid of the factorials. What's bigger, n or n minus 2? N is going to be bigger. So there's your n minus 1 and your n minus 2 over n minus 2 factorial. Those cancel there. Keep the equal 30 going on the right side. Now we have n times n minus 1 equals 30. Remember in the one above, we just left it like this? Well, now what I'm going to do is I am going to multiply through. I get n times n, and then n times negative 1 equals 30. The reason I do that, you may notice now we have a quadratic, and this is where you've been doing this for 2 years now, boys, right? We're going to be doing the factor solve, right? So we're going to make it equal to 0. And then we're going to factor n minus 6, n plus 5 equals 0. You get n equals 6 and negative 5. Now, in this case, you're often going to have one that doesn't work. Why does negative 5 not work? It comes from our definition earlier in the booklet. We can only have natural numbers only. Okay, remember, fancy word for all your positive counting numbers. So you can only have 1, 2, 3, 4 up to infinity, never a negative number, never a decimal or a fraction. So n equals 6 is the only possible answer. All right. Question 5 is pretty similar, so I'm going to leave that to you as well.